In this video, we're going to look at close packing structures, in particular solids. And these types of structures are typically observed when we have just metals. Okay, so there's no ionic interaction here between a cation and an anion. We're just putting metals, or the atoms of a particular metal, next to each other. And the particles in these solids are spherical and packed in the most efficient manner to minimize empty space. Okay, so think of a gumball machine here. There's no attractive forces between each of those gumballs, but if you look at a gumball machine, since all of the spheres are exactly the same size, they're going to pack in the exact same way each time you look at this gumball machine. So I've kind of drawn out here the first layer here, and remember, we're packing together to minimize empty space. So in one dimension here, the best way for these atoms to pack, or these spheres to pack together, are just to get as close together as I have them drawn here. And in layer 1, each sphere is surrounded by 6 others. And since we're looking at metals here, we are going to be looking at the same, in each case here we have the same metal. So if we focus on this sphere right here in the center, we can see that it's surrounded by 1, 2, 3, 4, 5, 6 other spheres. So this is what I mean by, in this layer we have each sphere surrounded by 6 other spheres. Now for the second layer, or layer number 2, remember these solids extend in 3 dimensions. So we need to now place another layer of spheres on top of this. Okay? It's not very likely that when I stack these spheres together that they're going to go exactly on top of the first layer. Think of oranges at the grocery store. We don't stack oranges directly on top of each other. They're going to fill in the spaces formed by the first layer. So in layer number 2, the spheres rest in depressions formed by the first layer. So in the second layer here, they're going to form in the depressions here between the other layers. So this is going to dictate how these particular atoms in the second layer are going to rest. Okay, so in the gray spheres that I shown here, these for layer number 2, they're going to rest right in the depressions, and if I would have went out in 3 dimensions, we could put a lot more atoms in here. But in this second layer, pretty much in every structure, we're going to rest in the depressions formed by that first layer. Now layer number 3 kind of gives us 2 options. So there's going to be 2 possible arrangements. Okay, and these 2 possible arrangements give rise to HCP and CCP, or hexagonal closed packing arrangements and cubic closed packing arrangements. So in layer 3, we have 2 possible arrangements. The first is hexagonal closed packing, which is abbreviated HCP. And here, the third layer packs over the first layer. And the repeat arrangement we get here is AB, 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 AB packing. So our first layer is just like drawn here with the 6 spheres surrounding each other. The second layer has these gray spheres go right in the depressions of that first layer. Then the third layer packs on top of that directly above layer number 1. So we call that AB, AB, AB packing. The second arrangement is called cubic closed packing, or CCP. And in cubic closed packing, the third layer packs over the holes formed by the first 2 layers. And this gives rise to ABC, ABC, ABC packing. Okay, so we have layer number 1, then layer number 2 goes right on the holes of layer 1. Then the third layer packs over the holes formed by these first 2 layers. So you get like a 3-tier set of packing here. Both cases minimize empty space and have 12 nearest neighbors. Or we can say the coordination number is 12 with 26% empty space. And if you look in your textbook, you'll see a chart that lists all the different types of packing and the percentage of the empty space and the various edge lengths, which will allow us to look at various relationships. And keep in mind that all these relationships are under the assumption that all the atoms or the spheres have the exact same size, which would correspond to structures of various metals.